simple. The recordings. Okay, I am presenting something relatively elementary and simple. Well, if you know the area, I guess. If you don't know it, then it looks probably more complicated than it really is. So this is a project that I started some years ago with my student Dongwei Chen. And it's a continuation of this. So some of the stuff you will see I did before he finished, and he's now at Colorado State University and soon at University of Idaho. Um, all right, so let me. Oh, this is not working. I don't know. Oh, okay, it works. Okay, I'm talking about something which is called frames, and in a thing which is not classical. Okay, what is a frame? It's simply something like a basis which has actually too many vectors. So it's a bunch of vectors which is essentially contains a basis. You are allowed to have more than you need for a basis. Okay, and I'm going to look. Um, uh, for those guys who are on Rn. I mean, these things have been done for Hilbert spaces, for example, infinite dimensional spaces. So this is a basically finite dimensional one, and that's good enough for us. And we want to look at something which is more general than a frame or some extension of it. I'm going to give you the actual uh, definition of a finite frame, and that's what you see right here. It is basically the bunch of vectors, and then you have this, right? So these phi i's n vectors, and then you take the Euclidean inner product and you square the values you get and you sum them from I equal 1 to n and the cardinality of the number of vectors you have. And what you want to see then is that you have an upper bound. Well, that upper bound is kind of trivial, okay? The more interesting thing is actually the lower bound, okay? So what you want is that you don't find any way that the vector that outcomes is zero, right? That would be exactly happening if you don't have a basis. So you can kind of recover the norm of that vector at least, okay? But eventually you have to multiply by a number which is relatively small, but it should be always positive. Okay, so the frame condition is really captured here. The upper bound, okay, is clear. The question that it exists, some upper bound exists, is clear, but the question here is a relation, right? A could be equal to B, for example, and then that what you call a tight frame. And if A equals B equals 1, then this is called a Parseval frame. These are two things that everybody in frame theory knows, okay, but likely people who are not in frame theory have never heard about it. But it's you will see some geometric way of understand all this during this talk, okay? I tell you it will be easier than this inequality. But first, we look at a generalization. And this is if you take Borel probability measures and then you can, the exponent may be p instead of 2, what you've seen on the previous slide. Okay, p is anything between 1 and infinity. Infinity, we don't want to allow, of course, because it doesn't make sense. All right. So you see here the you can basically ask the same things for the constants, okay? And I even didn't say that that a has to be bigger 0, so a little mistake here in progress. So I should have said a is bigger 0. But you see the condition is crazy. Is basically the sum is is essentially replaced by an integral and the vectors become a measure, okay? And so you have the same conventions. The tight probabilistic frame is A equal to B, and a Parseval frame if A equal B equal 1. But here you see that um, this condition with B is non-trivial because it could actually happen that your integral, okay, diverges. And what this means is the upper bound essentially implies that a probabilistic P frame has finite Pth moments. You can quickly show that this is pretty much the same. So you want to restrict for those guys. On the other hand, um, so yeah, I'm on the wrong track here, is what I'm saying. So basically, the thing why you do this generalization, you can embed finite frames in the space of measures using delta measures, okay? And this doesn't really make a lot of sense, okay, unless you are starting to talk about a distance between two frames. And let's look at this. So I have disorganized slides. I see here I put one in before that. Okay, so I will come back to this. Here I want to have an even more generalization. Okay, the previous frames depend on P. Okay, a P frame, but I want to throw that away and I just want to say something which captures it, okay? So, and it's basically a definition that you can that makes the definition of a frame a lot more geometric, and this is, I think, what it should be. That just doesn't work for infinite dimensions, for example, but it works quite well in Rn. Okay, so I want that a frame basically captures a basis property. And for measures, I can simply say, okay, the support of that measure should not be contained in any linear subspace of Rn. Because if it would be in a linear subspace, right, then all um, the points, all these the constant a in the definition would not be bigger zero. So you had basically, or think of finitely many vectors, okay, then it's clear. If they lie all in a plane and some plane, it's not a basis. Okay, so this is quite a reasonable definition. And then you can put the what's called the Levy-Prokhorov metric on these things, and uh, you get a metric. Don't worry about this thing. It will be of no further use. Okay, that's just for me to tell you. Okay, and this is not, this is typically, or this is untypical. So people did not consider that kind of metric. They all consider the Wasserstein metric, which will come soon. Anyway, you can do this and you can derive all these properties. Now I'm back to where I started talking about. We are going back to finitely many vectors, okay? And you want to compare them. Now you have a problem. If you have two frames, finite frames, and they have different cardinality, it's not easy to compare them, right? Because this distance, which you would take, for example, the sum of the squares distance for p equal 2 uh, doesn't like to have vectors, doesn't like to compare vectors with two different cardinalities, okay? And so basically, that alone makes it worth to basically go into the space of measures, and then you can use the Wasserstein distance. Okay, and that basically boils down to this distance when you take finitely many vectors, but it doesn't care about the cardinality. Okay. Now this one here is a little more involved in defining it, okay, because you have to know what couplings of two measures are. Otherwise, you take again an integral with the right two vectors, take the difference to the power of v, but then you have this measure that lives on R2n, right, which is called gamma, okay, and And so this coupling has a property that the marginals are mu and nu, so that connects them to the two measures you want to compare. Um, don't worry if you haven't seen all that, okay? It will not be of, well, there's a little bit depending on this, but I hope it is not completely unclear. So the only thing I can say that if you have an actual map, okay, that pushes mu to nu by sort of a push forward map. So you have a map and you push forward mu to nu, then you get one of those couplings. Okay, so that is easy to see. And there's always a coupling, okay, just simply the product measure. So these couplings are more general than maps, right? That's what that tells you. And it's actually allowed to spread mass. So to have, if you have a point mass, you can smear it out. You can basically spread it out over a bigger area. And so if you think that is exactly what the product measure is doing, it basically maps a single point to the whole, right? To the whole space. So this is how you can probably think about it. For now, it's not so important to understand the details. So if you if you use uh, the definition of a probabilistic space, and you can make those into metric spaces. Either use this Levy-Prokhorov metric or use the Wasserstein metric. But in any case, okay, here's something interesting about these guys. So if you have a probabilistic frame or a P frame, okay, it doesn't matter, okay, whatever it is, okay, then you have a couple of equivalences. And so the first one is the way how I did define the frame condition that the support of mu is not contained in any linear subspace. Okay, but there's another one, number three, if I see that correctly, that is kind of interesting for what I will later use. For any linear subspace, the push forward, okay, uh, the projection that is to that subspace, okay. Uh, so you take the projection to that subspace and you push forward a measure to that subspace. And if the measure, okay, uh, is a probabilistic frame, then its projection is 1, 2. Okay, on the smaller subspace, right? Whatever that is, it just has to be a linear subspace. Okay, and linear subspace is really important. Okay, you cannot have something that looks, let's say, a fine linear but doesn't go to zero. It really has to be a subspace. That's important thing here. Let's skip the other two conditions. I'm not going to use them that much. It's just an interesting theorem. If there would be something or proposition, if there would be somebody here who does frame theory, it would be probably worth to explain it. But I don't see anybody. But so let's move on. So one thing that was important for me to observe is that for any P, the set of probabilistic P frames is open in the topology generated by the two by the that should be P Wasserstein metric. It's a typo. It should be P Wasserstein metric. Okay. So um, this one was there before, but I think our proof is very different, and I think it states what it should say much clearer. So meaning, if you are taking a sequence of measures, okay, and you move towards a probabilistic frame, at a certain point, you will have a probabilistic frame, and that goes for any p. So that's a very good thing to know. And I just realized that this openness is true for the whole thing of for the whole set of probabilistic frames in the Levy-Prokhorov metric, but I have not written down the proof, but I checked it, and so it's got to be true. Uh, yeah, I already said what's coming. That yeah, I'm checking my time here. So basically, the you can use all kinds of analysis now because you deal with open sets. So that's the first thing. Um, and uh, I applied that with my student Dong Wai to some questions. Okay, and that was a very useful thing to know. Okay, good. So if we restrict ourselves to two frames, then you can write the inner product a little bit differently. If you write it basically thinking in a basis, okay, you write vectors as columns and rows. Okay, so then you can tear this integral apart into pieces. So basically, an integral that depends only on the variable you integrate over, okay, y, and the other variable x or vector um, that you can pull out by linearity of the integral. And then you integrate it and you get a matrix. And that is an n times n matrix, and it's called the frame operator. Okay, most of the people who do frames actually like to use two frames because you have this convenient frame operator. And that brings a little bit of geometry into this whole pictures. Okay. So you can first of all say what a frame is, okay? Because if you have a frame, then S mu is positive definite. If you don't have a frame, it will not be positive definite. So if it's a tight frame, it's the this matrix is lambda times in with some lambda bigger zero. And if you have a Parseval frame, if you remember, okay, then this frame matrix is in. So, so the thing is that when you see this whole story the first time, you think the Wasserstein distance is basically s- some choice, okay? It doesn't look very natural. See, because of the whole relation to these transportation distance, which is partly how you define these gammas, okay? So it looks quite weird, but then you discover that the Wasserstein distance is basically built in this frame ellipsoid, sorry, in this frame operator, okay? And so because if you take these projections, okay, to a plane, right, which is perpendicular to a unit vector x, and you push forward your measure and you take the two Wasserstein distance squared, then you see exactly the integral. Okay. And so basically, um, this integral or these matrix codes particular Wasserstein distances. All right. So they are all basically very naturally in there. And okay. So, well, if we have a frame, then the matrix S mu is always positive semi-definite, and so it has a root. And then you can define an object, okay, S mu to the power of 1/2 uh, times x, where x is 1. That's an ellipsoid, okay, or hyperellipsoid, basically, or full dimension because you have a frame, and S mu does not have eigenvalues of or has full rank. Let's just say it has full rank. Okay, so that basically gives you a lot of interpretation, okay, about the constants in the initial definition of a frame, okay, A and B. That makes this into something geometrical if you think about it for a moment. Um, so if S is not definite, okay, mu is contained in some subspace, and then the ellipsoid is still there, but it would be contained in that subspace. Okay, so you can basically see a lot of things just by looking of that thing. Okay, and then you have principal axes of this ellipsoid, and they correspond to particular Wasserstein distances, two Wasserstein distances, and in these eigendirections V. Okay. Um, so now I will come slowly to manifolds, and this is kind of a probably some sort of a step, and I have a few minutes. And we did not do much yet, and that is simply a question of time. I have another project which was probably fitting a lot better into the whole theme of the seminar today, which is about polygonal billiards. So that's related to many talks I've seen, but I decided to give this talk for some reason, hoping that I can tell you a lot more about the connection to manifolds. So let me just do something very simple. Some facts, okay? So first of all, these Wasserstein distances that you care about, because you can describe some of them very explicitly. The Wasserstein distances, right? If you change the unit vector, of course, depend differentiably on that unit vector, and there's a simple formula. Okay, everybody knows that, has seen that before, right? Okay. Uh, Another thing is, if you think about Riemannian geometry, right? I mean, if you want to define frames on manifolds, right? Particular vector bundles, because to define a frame, what you need definitely is you need an origin. You cannot just, well, define a frame without having an origin. So you need an origin in your space. You need an Euclidean structure basically, and decide where the origin is. So any fiber bundle has any vector bundle, sorry, not fiber bundle, vector bundle has something like that, okay? And then you typically have also Riemannian metrics. And this little lemma here, it's not even a lemma, I would call it also proposition. But so this thing here tells you that these Wasserstein distances, the p Wasserstein distances, are working well with a metric tensor M, right? So with an inner product on a manifold, or on some vector bundle on a manifold. Okay. So this is kind of good news, because if you wouldn't have this and also the previous differentiability, you would not have an easy time to do this. The other thing is as follows, because you can, if you remember this proposition with the 5 points I showed you. So basically, if you take a projection of a frame, right, you get again a frame. And that means you can equip these Grassmannian manifolds, right? If you take a probabilistic frame in Rn, and then you consider subspaces of Rn, like for example, the ones defined by the points in a Grassmannian manifold, namely all of them, right? Then you you kind of project your given probabilistic frame onto basically the plane defined by the points of Grassmannian, right? And you get basically a probabilistic frame on the tautological bundle of these Grassmannians. Okay, so this is how you can construct them, and from there you can do a lot more. I just haven't done it yet. Okay. I claim that you can do a lot more. Okay. Because, you have these maps from any, for example, embedded manifold, make Rn or n big enough. Um, and you will see that. Okay. So, sorry, I flipped back. This is basically the only thing I want to say in connection to manifolds. So there's definitely something you can do here. And if you just want to look at those Grassmannians, that's already enough. There's a bunch of questions that you can look at, and we just didn't move forward for time reasons. So the other thing which I found kind of interesting, and I have like 2 or 3 minutes, is the fact that there's something like transport duals. And this is like, in a way, like a dual basis. Okay, you can define something like that. This is a definition. I just give it because I don't have much time. This is a definition for probabilistic two frames here. And so there's an alternative definition. Um, it's just an integral, okay? And it's connected to actually the frame matrix, okay? The frame matrix or frame operator of that gamma. So gamma again is one of those uh, okay, forgot the name. Anyway, so these things, so you have a matrix and you have a condition, and that means you can generalize this. Okay, you can write an M in the off-diagonal I elements, and you can talk about M dual pairs. Okay, so this is quite an interesting concept because of the theorem down here that basically looks at the two measures, mu and nu, that are dual to each other's, okay? And a priori, you don't need to know they are frames. But if they are M dual, both are frames because of these inequalities, okay? So M duals basically come in packages. And what is interesting here, this is like the Heisenberg uncertainty relation, okay? I don't know if you have ever heard about it. As a physicist, you would have. And I think there's a lot more inequalities like this, but and it would be interesting to discover them some. So where you can see a Heisenberg uncertainty relation, okay? This is basically uh, the end of my talk. I have one or two more slides. These are just theorems about transport duals, and I skip over them because I'm the last speaker. Okay, and I don't want to keep you up. Thank you.